In this video, I'll be covering identifying minerals with a spindle stage. This will be using the orientation of planes relative to the optical vectors, and also the data that you collect automatically with the spindle stage, which is like 2V and optic sine. So first I'm going to do the 40-degree test to make sure this crystal is in a good orientation, and it goes extinct there, roughly. So it doesn't need to pass this test, but it's always good if it does, orientation-wise. And then normally what you do is start with extinction positions at 0 and 180 degrees for the reference azimuth, so that I have a good constraint on the east-west line. But notice in this case, this orientation, it's low retardation, and it's like near an optic axis or something is interfering with it. Could be those twin striae as well. But if that happens, I just rotate the specimen pin or whatever is holding that to the orientation that I want, so that I have a crisp extinction position for 0 and 180 degrees. Because if you're mounted looking down an optic axis, you might count a bad extinction position twice, and we don't want to do that. You just want to cross a couple of bad values and not count them double, which can happen. So I have to realign this a little bit after I rotated the specimen pin, and this is looking pretty good. I'll focus this. Just going to bring the rotation axis a little bit up. Lock the stage. And move the rotation axis up with this screw. And this could all be done with a simple spindle stage as well, just like a cardboard one, but not nearly as precisely. But you can index planes and get an optical orientation solution with a cardboard spindle stage, but this one is just much better and more precise. So this is looking good. So now I'm going to just show that nothing changes. It'll still pass the 40-degree test. That doesn't change anything when you just rotate the spindle axis on how the specimen pin holds it. It's just a way to prevent the 0 and 180 degree duplicating a bad value for the extinction positions. So yeah, I'm going to just measure this extinction position for 0 as you would. I'm going to enter this in on the computer. 196.4. And then I like to just skip on down to 180 degrees and do this right off the bat. That's my ritual. Just repeating the process. And then entering that in. Then I'm going to use that suggested reference azimuth. And then we're just going to do this a bunch of times for 10, 20, 30 degrees and so forth, the spindle stage. Measure a bunch of extinction positions, and then we will also correct some of the erroneous values that you run into, which can happen when you cross an optic axis, or it's just you accidentally messed up the measurement. I always like to go back and see what the bad values are in the ES minus calc column. So this one is negative 2.9 degrees away. So that was not the best value, even though this data set is good overall, I'd say. So I might just go and remeasure a few of these just to fix Sometimes you don't have to, but like if the crystal has high dispersion or you're crossing an optic axis, you're bound to have some values that aren't as good. And I like to go and fix those, just recheck them under the microscope. So once we do that, there's a few things that you notice on the spreadsheet though. There's a new test on the right, or kind of in the center there, uniaxial versus biaxial. It'll suggest whether or not it's uniaxial or biaxial using the extinction curve as a measure. If the extinction curve is like roughly a great circle on a stereo net, it's probably uniaxial. So I added that in there if you're dealing with an unknown like this. In this case, I mean, I do know what it is, but we're treating it as if it was an unknown. The next thing is optic sign. Here I'm just aligning the acute bisectrix line east-west and then rotating 45. So now that I've done that, insert the wave plate. It adds, so this is optically positive. Acute bisectrix is optically positive. So the gamma refractive index is the acute bisectrix, or Z in terms of vector directions. The next thing I'm going to do is I'm going to index the twin plane that I see here. And you probably already, you may think that this, you may already know what this is. This is a plagioclase crystal. It has those distinct twin planes, these polysynthetic twins. And I'm indexing those as my plane. It could be a cleavage plane or a twin plane. But if you index a plane on this new version of the spreadsheet, the database in one of the tabs will use that bit of information for comparing the minerals that are in the database to your unknown crystal to figure out what it is, or try to. Because what we figured out is optic sign, 2V angle, and now we're getting an orientation of a plane relative to the optical indicatrix orientation, which really actually narrows it down quite a bit if it is a biaxial mineral, because we also constrain that, whether or not it was uniaxial or biaxial. So with just a few pieces of information, we can constrain it. So yeah, I've gone over this procedure before, but you're just aligning a plane so that the pole to the plane is east-west. And I'm entering this plane in. You can enter in two planes right here if you want. I also forgot to name it. You can name it and it'll plot where the plane is on the stereo net. And once you do that, you can go to the database tab. It's not finished, but there's a bunch of minerals in the database right now, and there's some minerals that vary in their mole fraction, like plagioclase, and you could see that it's scoring them based on how well the properties that you measured or determined match up with the ones that are in the database. So in this case, you can see it matches with optic sign and the orientation of the plane really well. It also matches with 2V. So out of 3, these are scoring around 2.9, and so not only are we getting what the mineral species is, we're getting a composition, because plagioclase optical orientation varies with composition. So yeah, I would say around AN65 labradorite is what this crystal is, and we figured that out with just those 3 bits of information, just determining the optical orientation and the plane, 2V, and the optic sign. So, and you can also enter, if you measure refractive indices, you can also do that. It'll score it even higher for alpha, beta, and gamma. But just a demonstration of what you can do identifying minerals. But that's it for the database.